Hey folks, welcome back. In this video we're going to look at a summary of the simple harmonic motion formulae that you need to be able to use. So let's get started. So if you look here, you'll see a big table full of all the equations or relationships that you need to be able to use in the exam for simple harmonic motion. So if we start with displacement first of all, remember we have two expressions for displacement depending on what the initial conditions are. We say that y equals a sine omega t when the initial conditions are y equals 0 at time t equals 0, i.e. before the object started moving. If it begins at the equilibrium position or rest position y equals 0, then we would use this one here. However, if the initial conditions are y equals a at time t equals 0, i.e. if the object starts at a maximum amplitude away from the equilibrium position of the object's motion, then we use y equals a cos omega t. So we use sine for y equals 0 at t equals 0 and cosine for y equals a at t equals 0. We then saw two expressions for angular frequency in terms of linear frequency and the period t of the oscillations. So these were omega equals 2 pi f and omega equals 2 pi over t, which you get on the relationship sheets. And remember we saw these in the rotational motion topic as well. We then have velocity with three expressions here. So the first one, v equals a omega cos omega t, that is found, remember, when we start with the displacement expression y equals a sine omega t when y equals 0 at t equals 0. And if we differentiate that y with respect to time, we end up with this expression here. And remember that can be very useful when we're deriving things like the general velocity expression here. We also saw that maximum velocity was when we have omega times a, i.e. v max equals omega times a or a omega. And we also derived an expression for velocity in general, which was plus or minus omega times the square root of a squared minus y squared. So remember, you could be asked to derive that in the exam, so make sure you can go through the steps. We then have acceleration with two expressions here. So remember the equation for SHM or definition of SHM is shown by this equation here, a equals minus omega squared y, because this tells us that the acceleration of the object is proportional to the displacement y, but in the opposite direction shown by the negative sign, which is basically what Hooke's law told us in terms of the unbalanced force or restoring force being proportional to the displacement, but in the opposite direction. So this technically tells us the definition of SHM. We then have an expression for maximum acceleration, or A max, which is equal to omega squared a, which remember we derived in the theory video. Next we have kinetic energy with two expressions here. So remember this one appears on your relationship sheet. Ek equals a half m omega squared times a squared minus y squared, but you need to be able to derive that for the exam. And remember you just start with Ek equals a half mv squared and you sub in the expression here for velocity. We also have maximum kinetic energy when y equals 0 at the equilibrium position, so Ek equals a half m omega squared times a squared, and that's just this one that's simplified slightly. And lastly, we have an expression for potential energy, which you can derive using conservation of energy, but you don't need to be able to derive it for the exam. So we have EP equals a half m omega squared times y squared, which is a wee bit simpler than the general kinetic energy equation. That's all for this video, folks. I hope you found it useful. If you did, give it a like, subscribe to the channel, and I'll see you in the next one. Take care.